Today, we're going to explore the renewed relevance of rammed earth construction. The ideas here are drawn from the work The Memory of Rock, Understanding Rammed Earth by Gokul Salvadi. And the central idea is pretty simple. The material itself hasn't changed, but the world we build in has. And that's made its inherent properties newly valuable.
And this is really the fundamental starting point. We're not discussing some new technology here. The science of compacting earth to create durable walls is ancient. It's a process builders have understood for centuries, long before we had the language of modern material science to describe it.
So, that brings us to the real question. If the material itself is the same, what's shifted? What's changed in our environment, our economy, our understanding of health that makes us look at this ancient technique again? It seems the value isn't in the wall itself, but in how it relates to the world we live in now.
To answer that, we first have to understand the new set of problems we expect our buildings to solve. The pressures on construction today are profoundly different from what they were even half a century ago. Well, for one, the cost of energy is no longer a small detail in a building's life cycle. In a lot of places, you have rising utility prices, plus climate-driven realities like longer heat waves and urban heat islands. All of this creates a really strong economic case for buildings that can stay comfortable without running the AC all the time. A building that can passively manage its own temperature is now a major asset. Then there's the issue of supply chains. Conventional building materials, cement, steel, they tie a project to these complex global networks. And those networks are vulnerable to disruptions from fuel costs, international trade, problems with resource extraction. This dependency just introduces a huge element of risk and unpredictability into the whole construction process. We're also just much more aware of our indoor environments now, especially since the pandemic. Things like proper ventilation, humidity levels, and the off-gassing of chemicals from synthetic materials, these are now understood as direct health concerns, not just matters of comfort. And finally, there's the problem of waste. Cities are really struggling to manage the sheer volume of construction and demolition debris. Every conventional building we put up represents a future waste management problem, a stream of material that will eventually have to be dealt with, often at a very significant cost. So, having laid out this new context of problems, energy, supply chains, health, and waste, we can now turn back to rammed earth itself and look at how its basic properties offer a direct response to these pressures. This really illustrates the mechanism of its resilience. Rammed earth construction basically decouples a building from all those external markets. The main material is the soil right there on site, and the processing is mechanical, not chemical. This localization acts as a kind of insulation from global price shocks and supply disruptions. It's a practical form of insurance, not an ideological one. Now, this property directly addresses that issue of indoor air quality. A vapor-permeable wall can actually absorb extra moisture from the air when it's humid and then release it back when the air gets dry. This process passively buffers the indoor humidity, which helps maintain a more stable and healthy environment without needing a machine to do it. Essentially, it lets the building breathe. The building process itself also addresses some of those key pressures. Because it's a labor-intensive method, it tends to create local employment. And as for waste, the material cycle is completely closed. Any unused soil or even debris from a demolished wall can be returned right back to the earth without causing any pollution. Which brings up a pretty logical question. If the logic of this material is so sound, why was it ever abandoned? The answer seems to have a lot less to do with how it performs and a lot more to do with how it was perceived. When concrete became widespread, its image was compared to Earth's image. Concrete was sold as the look of modernity, of progress. A direct scientific comparison of performance, well, that was largely absent from the conversation. The key questions: how does it perform thermally? How does it regulate humidity? What's the embodied energy needed to produce it? Those weren't, for the most part, simply not asked. It was really a victory of marketing, not of material science. And this brings us right back to where we started. The material has just been there, unchanged, waiting for our context to shift. The resource was never scarce. It was just overlooked. It was buried under a completely different set of priorities and a different idea of what progress was supposed to look like. And it seems the conditions we face now, our energy needs, our health concerns, our fragile supply chains, have finally caught up with the logic that was inherent in this ancient material all along, forcing us, perhaps, to take it seriously once more.